project is the nation's manned orbital spaceflight program being conducted by the National Aeronautics and Space Administration. The project involves a continuing, broad research program. The Mercury capsule shape was determined from intense scientific and engineering investigations using a wide variety of technical equipments. The moment of inertia on test models was determined on this pendulum rig. Wind tunnel tests of small and large-scale models have been carried out, covering a speed range from 0 to 18,000 miles per hour. Small models of the capsule were fired in this supersonic free-flight ballistic gun range. In the gun, helium compressed by a powder charge accelerates the 1-inch model down a 30-foot instrumented range of recording stations. The model achieves speeds of up to 10,000 miles per hour. Data are recorded by means of special cameras located along the length of the range. As the model speeds down gun range barrel, graphs and shadow graphs are acquired. This shadow graph, taken at one of the recording stations, clearly shows the flow of air passing around the model at supersonic speeds. Detailed analysis of data acquired in tests of this nature provide a solid basis for proceeding to more complex tests and to improved versions of the capsule shape. In other tests, a small model was instrumented to measure the scorching heat of re-entry as simulated in a shock tunnel. The air in this tunnel rushes past the model at 14 times the speed of sound. The severe heating ionizes the air in the region of the heat shield, causing it to glow. In another wind tunnel facility, free-falling models were used to determine the best attachment points for the parachutes. And a detailed picture of the flow of air over the capsule at relatively low speeds was obtained by observing the movement of pieces of yarn glued to the surface of the model. Full-scale capsule models were tested in a large wind tunnel to determine the capsule's lift, drag, and pitching moment characteristics. The validity of the Mercury configuration had to be established not only for the capsule alone, but also for the capsule with the escape tower. In a typical wind tunnel experiment, a scale model of the escape configuration was tested over the speed range from 1 1/2 to 4 1/2 times the speed of sound. During the test, the model was forced to oscillate to determine its dynamic stability characteristics. In other tests, the effect of the Mercury capsule on the performance of the various boosters to be used in the program was investigated. The static stability of the capsule fitted to an Atlas booster was determined in a 9 by 7 foot supersonic wind tunnel. Wind tunnel tests were of particular importance in the case of the Redstone booster. The Redstone is an aerodynamically stabilized vehicle, as is evidenced by the large tail fins. In these tests, it was determined that the booster would coast along a stable path, even if the rocket engine was suddenly shut down. The stability of the Little Joe booster with the Mercury capsule and escape system installed also had to be established. In the wind tunnel testing program, Mercury experiments were performed in 26 different wind tunnels of the National Aeronautics and Space Administration and of the Armed Services. 70 separate models of various sizes and configurations were constructed, and 106 tests were conducted. In each of the 106 tests, a number of variables, such as Reynolds number, Mach number, and angle of attack, was investigated. But wind tunnel tests alone are insufficient to solve all of the many problems associated with the Mercury flight system. A flight test program using full-scale models of the Mercury capsule was therefore initiated. These boilerplate models, which are made in NASA shops, duplicate fully both the weight and the external shape of the final Mercury operational capsules. Their construction is greatly simplified through the use of heavy welded sheet metal. They do not include many of the Mercury subsystems, such as the life support system or the communications equipment. These boilerplate capsules have been used to develop the parachute system, to validate recovery procedures, to check the functioning of the escape system, and to determine the motions and heating of the capsule during re-entry. Large cargo airplanes were used in the development of the parachute system. Full-scale boilerplate capsules were dropped from Air Force C-130 aircraft at high altitudes. The capsule slides out of the plane's cargo door on a sled. As soon as it is clear of the aircraft, the sled is released. And after a period of free fall, the lid on the antenna canister is released. Then the small drogue parachute is ejected by a mortar charge. This parachute reduces the capsule's swinging motions in the early stages of the descent. At a predetermined altitude, the small parachute pulls the top antenna housing away from the capsule and automatically deploys the main descent parachute. The capsule then descends toward the water. The main descent parachute is a 63-foot ring sail type cargo parachute. Upon impact on the water, the parachute is released from the capsule by a small explosive charge to avoid dragging the capsule in the wind. The airplane drop tests also provide an opportunity to exercise the various recovery devices and to further develop and improve recovery operational procedures. After impact, a smoke generator is energized to emit smoke from the tops of the capsules to aid the visual search. This is a view of the capsule from an approaching recovery vessel. A green dye marker solution is released from the base of the capsule to help make it visible from greater distances and altitudes. And a small antenna on top of the capsule transmits signals from the automatic rescue beacons to searching ships and aircraft. Concurrent with the airplane drop test, an extensive rocket flight test program has been initiated. At the National Aeronautics and Space Administration's launch site at Wallops Island, Virginia, tests were performed to develop the emergency escape system and qualify it for future use on manned flights. Escape from the launching pad can be simulated by lifting the capsule from the ground with the escape rocket as the only means of propulsion. After ignition, the escape rocket burns for only 1 second. It appears to burn much longer here in this slow-motion sequence. In an in-flight abort, the capsule would be carried at least 250 feet away from its booster. The capsule and the tower then coast together to the peak of the trajectory. The gentle rotation is caused by a deliberate offset of the rocket thrust to provide a lateral displacement of the capsule as it leaves the booster. This rotation would impose only small loads on the pilot inside the capsule. At the maximum altitude, the tower is separated from the capsule with a small rocket. Then the antenna housing lid is released. And the small drogue parachute is ejected by the mortar charge. After the swinging motions of the capsule have been reduced, the drogue parachute and the antenna housing are jettisoned, automatically deploying the main descent parachute. On impact, the parachute is automatically disengaged from the capsule. In an off-the-pad abort, the capsule reaches an altitude of more than 2,000 feet. The main parachute was deployed and opened fully above 1,000 feet, providing ample time for the use of the reserve safety parachute if required. In these tests, the capsules were recovered by helicopters and returned to Wallops Island for further use in the test program. The tests also provided an opportunity to conduct development work on the recovery and pickup techniques. Other flight tests are being carried out with a series of booster vehicles of increasing size and capability. The smallest of these is the Little Joe booster. The Little Joe airframe, produced especially for Project Mercury by the North American Aviation Corporation, houses 4 large Castor solid fuel rockets and 4 smaller Recruit rockets. The holes in the base of the vehicle indicate the relative sizes of these rockets. The Little Joe booster is unguided and derives its aerodynamic stability from 4 large tail fins. One of these fins is shown here as it is being assembled on a special fixture. Preliminary testing of the completed airframe is accomplished in a static test tower at the North American Company plant. The use of the Little Joe boosters in the Mercury development program provides an economical means for simulating many of the most severe launch, emergency escape, and recovery conditions. Final assembly of the booster takes place at Wallops Island. First, the rockets are erected, then the airframe is fitted around them. The capsules used in the early phases of the Little Joe program are manufactured in NASA shops and do not contain many of the systems and subsystems that will be part of the Mercury operational capsules. The escape tower and rocket, however, are final production hardware, being qualified in the Little Joe test program. In the fall of 1959, 3 Little Joe vehicles were launched successfully. The first was a test of the basic booster system. In the second test, the escape mechanism was activated intentionally during the early phases of flight. This test simulated a severe escape condition that could occur in an orbital flight launch. The capsule was recovered undamaged shortly after landing. The third flight was used to perform an escape maneuver at high altitude. After a planned escape, the capsule coasted to an altitude of 55 miles and was recovered 200 miles from the launch site. On this flight, a small monkey was within capsule and was recovered alive and well at the end of the flight. Before the firing, the scaffolding is removed and the booster is supported on a simple launcher. On takeoff, 2 of the casters and 4 recruits are ignited, giving a thrust of 1/4 million pounds. The smaller recruits burn for only 1 second, while the casters have a burning time of 27 seconds. The second pair of casters will be ignited just before burnout of the first pair, but at an altitude too high to be visible from the ground. The remarkable stability of the Little Joe booster is well demonstrated in this flight. Later on in the flight, the escape rocket is ignited, separating the capsule from the booster. At the completion of the escape sequence, the capsule falls back toward the ocean and parachutes are deployed. Recovery is accomplished by Navy ships. After recovery, the capsule is hoisted on board with a special net-like device and returned to NASA facilities for visual inspection and for an analysis of the data recorded during the flight. The Atlas booster was used in the most severe test of the Mercury system that has been performed to date. In that test, a research and development version of the capsule was launched from Cape Canaveral, Florida. In contrast to the Little Joe vehicle, the combination of the developmental Mercury capsule with the Atlas booster was nicknamed Big Joe. The trajectory for this flight was shaped to simulate a return from orbit without actually going into a satellite orbit. The objectives of the Big Joe test were to check the capsule's heat protection at nearly orbital speed, to verify its aerodynamic stability, to provide a severe test of the onboard recovery system, and to develop recovery procedures in a realistic test situation. The Big Joe capsule was taken to the launching pad several days prior to the shot. Within the capsule is special instrumentation to measure the loads, noise, motions, and temperatures during flight, and a control system to orient it into the proper attitude after its separation from the booster. As the capsule is hoisted to the top of the gantry, the plastic heat shield designed to dissipate the tremendous heat of re-entry is clearly visible. The capsule is mated to the top of the Atlas booster and attached with a special clamp. The clamp will be released explosively after the Atlas engines are shut down. The special Mercury capsule used in this test was not fitted with an emergency escape system. The booster and capsule systems and their instrumentation were checked and rechecked during the days prior to launch. The Joint Defense Department Recovery Task Force was deployed along the capsule's intended flight path. The launch was made in the early morning hours so that a full day would be available for recovery operations if required. In the blockhouse, the countdown proceeds for many hours before the firing. Here, the function and readiness of thousands of component parts of both the booster and the capsule are recorded. The malfunction of any one of these parts could make the difference between a successful flight and a complete failure. Minutes before the firing, liquid oxygen is piped into the booster, which is now ready for flight. As the countdown approaches 0, the final switch is closed and Big Joe is launched. This Atlas booster carried the capsule to an altitude of 100 miles and to nearly orbital speed. The Big Joe capsule was then separated under conditions that closely simulated orbital re-entry. On the recovery ships, the capsule appeared as a flaming fireball as it streaked back into the atmosphere. Many hundreds of miles from Cape Canaveral, airplanes vectored to the impact area and soon picked up the capsule's recovery signals. 2 destroyers raced to the area and sighted the capsule about 8 hours after launch. The capsule was picked up by the destroyer Strong and returned for a detailed inspection and for an analysis of recorded data. It had survived its re-entry in excellent condition. The recovered Big Joe capsule represents a major milestone in Project Mercury in that it positively demonstrated the validity of the Mercury design concept. Early in 1959, a team of 7 engineer test pilots was selected for Project Mercury. M. Scott Carpenter, L. Gordon Cooper, John H. Glenn, Virgil I. Grissom, Walter M. Schirra, Alan B. Shepard, and Donald K. Slayton. Following their selection, the men reported for duty with NASA's Space Task Group at Langley Field, Virginia. Their training, which has been in progress since April 27, 1959, includes both academic classroom instruction and practical experience in training devices across the country. The academic program includes instruction in the basic sciences related to spaceflight, astronautics, with detailed studies of propulsion systems, electronic systems, guidance, trajectories, and other technical aspects of rocketry. In addition to a penetrating study of the physiology of flight, the astronauts are being educated in the basic skills required to make scientific observations during orbital flight. As the training program progresses, the development and production of special flight equipment has continued. Each astronaut has been fitted with a custom-made couch developed to support his entire body and reduce the physiological effects of high acceleration forces, or Gs. To make the couch, the astronaut is placed in a bed of special quick-hardening sand. After the sand is carefully packed around the astronaut's body, carbon dioxide is applied to speed up the hardening process. At the end of the 2-hour-long couch molding process, the astronaut is carefully lifted out of the mold. These Mercury couches were produced at NASA facilities with painstaking care to assure proper fit and effectiveness in protecting the pilot during flight. During re-entry into the Earth's atmosphere, the Mercury capsule will be subjected to intense frictional heat. One of the early practical training activities for the astronauts provided familiarization with high heat conditions and the ability of the ventilated full-pressure suit to keep them cool under these conditions. This heat chamber is capable of producing the same temperatures anticipated inside the capsule during the re-entry from orbit. quartz tubes along the outer walls provide the chamber with heat. In this test, the pressure suit ventilation system was turned off to familiarize the astronaut with his own physiological reaction to short periods of high heat. In Project Mercury, the pilot will play an active role in the operation of the Mercury satellite. He will be able to control the capsule's attitude. He can maintain current knowledge of his position visually and through the use of radio navigational aids. He will be able to operate all primary flight controls, such as the firing of the retro rockets to begin his descent toward the atmosphere and to deploy the parachutes once he has re-entered the atmosphere. Wherever possible, the capsule's flight performance is simulated on the ground to provide realistic, economical training for the astronaut. In this fixed-seat analog simulator, instrument readings indicating a simulated capsule attitude are supplied by an analog computer. The pilot responds to the instrument readings by applying the proper control movements with the sidearm controller. In flight, this controller would activate small reaction jets to turn the capsule about its three primary axes. On the simulator, the control movements feed signals to the computer and result in changed instrument readings, portraying the kinds of capsule attitude changes which would have resulted from control movements in flight. Training on such simulators, the astronaut developed skill in maintaining the capsule's orientation during orbit, retrofire, and re-entry. Following the indoctrination on the fixed-seat static simulator, the pilots will be trained on a dynamic simulator. On this device, the astronaut will be supported in a molded couch. His sidearm controller will be connected to a system of reaction jets similar to the ones in the Mercury capsule. These jets will rotate the couch or pitch it up, down, or sideways. An intricate system of motion picture displays will give a view similar to that seen by the pilot in orbital flight. A special feature of this simulator is a low-friction air bearing designed to permit movement in all directions around a center post. One of the most important phases of the pre-flight training is that received on the centrifuges at the Wright Air Development Center and at the Aviation Medical Acceleration Laboratory at Johnsville, Pennsylvania. These centrifuges have the capability for reproducing the same acceleration, or G forces, on the same timescale as will be encountered during rocket-boosted launch and re-entry into the Earth's atmosphere. In this training, the astronaut learns more about the effect of these G forces on his ability to perform essential in-flight functions and what he can do to overcome those forces. While whirling around in the centrifuge cab, they learn new techniques of breathing and straining so that they can tolerate these high G forces while still performing functional control tasks. The centrifuge is operated in response to signals provided by a computer. The sidearm controller also gives electrical signals to the computer. These signals are translated into motions the reaction jets would have given to the Mercury capsule in flight. These signals result in changes in G forces within the centrifuge cab comparable to those encountered in actual flight. The test demonstrated that a properly trained man in good physical condition would be able to control the Mercury capsule even while being subjected to the high G forces of launch or re-entry. In other procedural trainers, the astronaut will be checked out completely and repeatedly in all of the procedures and operation of the capsule. In January 1959, the McDonnell Aircraft Corporation was selected as the prime contractor to design and construct the Mercury capsules. The selection was based on an industry-wide competition. In the course of this competition, 12 firms submitted proposals based on NASA specifications for the capsule. After a thorough evaluation of these proposals, a contract was awarded to McDonnell. An engineering mock-up of the capsule was completed by McDonnell in March of 1959. The mock-up was complete in every detail, including the escape tower and rocket, the antenna housing, the parachute container, the capsule proper, and the adapter ring that connects the capsule to its booster. The mock-up also included cockpit equipment and control layouts. Engineers and officials from NASA met with contractor personnel to assure that specifications governing the capsule design and the installation of equipment and components were complied with. Special attention was paid to the pilot support system and to the type and location of pilot displays. After the mock-up inspection had been completed, an official mock-up board consisting of NASA officials and military and aeromedical advisors made final recommendations. The Mercury astronaut trainees visited McDonnell shortly after they reported for duty. All engineers, these men are making a positive contribution to the design of the capsule and determine that all of the capsule systems are compatible with manned operation. Working with the mock-up, the astronauts review the pilot displays and check on the accessibility of controls, supplies, and emergency equipment. The location of windows and the ease of entry and exit through the main and emergency hatches was also studied by these men. Construction of the capsules was started immediately. Special welding techniques were developed. An argon atmosphere fusion welding machine is used in the fabrication of the thin titanium pressure vessel. The shell is carried past a circular electrode by rotation of the fixture. The pressure vessel consists of a smooth inner skin and a beaded outer skin. Each of these is only 0.010 of an inch thick. After the two skins are welded together, stringers, window and door frames, and bulkhead rings are installed. An additional skin will be attached to the stringers. Many of the component parts of the capsule are made by subcontractors under McDonnell supervision. The all-important heat shield is manufactured by the Cincinnati Testing Laboratories. This ablation-type shield is made to the same specifications as the one that survived the Big Joe re-entry. During re-entry, its surface will char and slowly burn away. Through this ablative action, the heat of re-entry will be dissipated. Other major subcontractor items are the life support system, the attitude control system, the horizon scanner, the escape and retro-rocket systems, parachute landing systems, batteries, and the navigation periscope. The periscope, which is shown in this sequence, is manufactured by the Perkin-Elmer Corporation. With the aid of this periscope, the pilot will be able to perform the functions of attitude stabilization and control and fire his retro-rockets, even if all of his automatic systems should fail. He will be able to determine his attitude, his orbital track, the ellipticity of the orbit. Once he has made a precise determination of all of the orbital elements, he will be in a position to fire the retro-rockets at the proper instant so that he will land in the prescribed recovery area. An operation as complex as that of putting man into space requires a great deal of ground support equipment. The equipment for this ground support is being developed by McDonnell and its subcontractors. A typical example of this type of ground support equipment is the array of electronic instruments to be used in the checkout of the capsule's communications gear. Once the capsule is in orbit, the pilot will rely completely on his various channels of communications, such as the radio voice transmitters and receivers and the various tracking and rescue beacons. His actions will be monitored by other communications channels, and certain capsule functions will be commanded from the ground. The proper functioning of all of this equipment can be guaranteed only by checking every detail during the days, the hours, and the minutes before launch. Similar equipment is being fabricated to check all of the other capsule systems on the ground and to monitor their functions during flight. The ground support equipment will be installed in a number of trailers so that it can be transported to the launching site and utilized in several different locations. Because both Redstone and Atlas-launched Mercury flights will take place concurrently, some of the equipment must be duplicated. 2 of the trailers shown here will house checkout equipment, while telemetry receiving equipment will be installed in 2 more. A 5th trailer will contain spare parts. In the fall of 1959, many of the capsule components reached the final assembly stage. The housing for the 3 retro rockets is equipped with a shield and with insulation to maintain the rockets at the proper temperature and to protect them from meteorite damage. A number of the top antenna canisters have been manufactured and are ready for the installation of their electronic components. Several of the escape system towers have been assembled and prepared for shipment. Some of these have been flight tested in the off-the-pad abort and Little Joe experiments conducted at Wallops Island. Final fabrication of a number of capsules is well underway. On the production line at the McDonnell plant, several capsules are in various stages of construction. On this line, the pressure vessel is fitted with the upper and lower pressure bulkheads. A large number of brackets and fixtures is installed for the support of the capsule's subsystems, the wiring, and the reaction control fuel lines. At the top of the capsule, the emergency exit hatch is visible. Windows and entry hatch are located along the sides of the shell. After the capsule fabrication is completed, the various subsystems will be installed. The assembled capsules will then be subjected to an intensive environmental testing program. The entire system must be able to withstand extreme heat and cold, high pressure and vacuum, vibration and noise, high accelerations, and all of these tests will be performed on the ground before the capsule will be certified as being ready for flight. Project Mercury, the nation's manned orbital spaceflight program, is a continuing program of concurrent efforts in research, development, engineering, manufacturing, test, and training, all aimed at the focal point of successful manned spaceflight at the earliest possible time.